Okay, can everyone hear us?
Yes, we can hear you.
Hello?
Yes, we can.
Hello?
Dan said on the chat that you can.
Okay, perfect.
But if we can't hear the people, that's also kind of bad.
We should be able to hear them, but yeah. Wait, yeah, I think it's this one. Okay, can someone try speaking again?
Oh yeah, can you hear us?
Let me try to connect.
Hello. Hey, did you ask for Zoom? So on Zoom we hear you. We hear you all the time. That's good.
Okay, hello everyone. We're happy to have you all here. We have with us Marian, who's studied as a research fellow at CERN starting last May. He has been a member of LHCb since his PhD, which he did at the University of Heidelberg, and then he did his postdoc at the University of Cincinnati. He is very involved in the trigger software, and he does extensive contributions to more, and he's currently the trigger liaison for the CHARM working group. So we're happy to have him here today, and he's going to give us a talk about real-time analysis here at LHCb. So I hope you have fun time, and if you have any questions, just let us know. So I'll hand over to Marian now.
Okay. So I'm very happy to be here, and it was a lot of fun preparing this talk. It's called From Collisions to Offline Analysis. So the last stage was given by Louis on the detector, and this is about the real-time analysis. So I want to start with an overview of the challenge, of the answer that LHCb has given to that challenge, how the data flow works in RTA, and then later I was going to. I think the slides are shared in Zoom. Okay. Yes, and I think when I will go slowly through the slides. I will try to explain well what I have prepared. But whenever you have a question, please just ask the questions in between. I've seen you have some Q&A in the end, but I think it's actually nicer to have this during the talk.
Recording.
Okay. let's start with the challenge. You have seen the detector in the last presentation, in the last presentation of this series. And Louis touched already upon what the challenge is. So LHCb is interested in beauty and charm physics, and what you can see here is a plot of the LHCb simulation, just simulating BB bar pairs, CC bar pairs, SS bar in the LHCb acceptance. And what you can see here is that the rates are enormous. We are talking about 1 million charm decays per second. And the problem is we don't have infinite money, and we cannot write out this data all to disk. If we would do that, we would end up with the budget we have. We would end up at around 50 kilohertz, and this is so this is a kilohertz here, and then we would end up somewhere here. So we would lose a substantial amount of all our beauty and charm signals. So what the challenge is then about is that we need a very flexible trigger to write out really those events that are interesting for us. And this is also needed to be a very flexible trigger because the LHCb's physics program has vastly expanded. So in the past, run 1 and 2, we had a level 0 trigger, and this limited us in very many analyses. And so the flexibility here comes from the fact that we can read out the full detector at a PP collision rate of 30 megahertz. So this is a very technical slide, but this is the concept of the trigger system. It's a full software trigger. The detector here is read out, as I said, at 30 megahertz. The output of the detector front ends is passed on to the event builder network. And in the event builder network, we have HLT1 running on GPUs. So currently there are 170 event builder servers, and they are equipped with 1 GPU each. Next year, or I think in the course of this year, the second GPU will be installed, and we will have around 340 GPUs running in the event builder. So this also increases our potential again, what we can do with the trigger. What happens here, I will explain in detail later, but the output of HLT1 is buffered on disk, and we have currently about 30 petabytes of disk storage. So you see here the event rate is around 32 terabits, so 4 terabyte per second, and is then reduced by HLT1 to about 1 megahertz, which corresponds to 1 terabit per second. And from this buffer, the data will then be further processed by HLT2. Okay, so this is a heterogeneous architecture. We have GPUs here, we have CPUs here. They all need their own software, and then there's some offloads. So Velo clustering is done on FPGAs in the event builder. I think Sci-Fi does also clustering in the front end, and so on.
Can I suggest something? Can we switch over to this so that we can hear people in Zoom? So I'll just...
Okay.
Can you still hear us?
Yeah, we still hear you on Zoom.
Okay, perfect. Yeah. So this should work like this.
Yeah, so we can hear people if they have anything to share. Thanks.
Okay. This is now a very similar picture, but focusing on different aspects. Again, we have the LHCb bunch crossing happening at nominal 40 megahertz. 30 megahertz of that are non-empty. The detector is fully read out. Then HLT1 is writing out with about 1 megahertz to the disk buffer, and from the buffer we can run real-time alignment and calibration. We can also run some monitoring from there. and then from the buffer, the data is taken by HLT2 and processed, and HLT2 can write out about 10 gigabytes per second. And it can do this write out, it can do this streamed. So we have here calibration and full events, and they will be written to tape. And then we have turbo events, they will be written to disk and distributed on the tier 1 sites on the grid. So you can later directly run on these turbo events, but you cannot run on the full and calib events. There will be some offline processing step, and this will be shown on the next slide. So the flexibility here comes in as essentially everything in this here in the HLT1 and HLT2 box is fully configurable and is fully configurable by everybody. So if you have a new idea of some reconstruction or some selection you want to run, you can make a merge request, and this will be reviewed, and then it can be run in the trigger. Yes, and I also touched upon the monitoring. The monitoring can be run from almost any of this stage. And there are some, so the how much can we actually write in these errors? This is also not fixed. This is also something that is flexible within some margins. Okay, this is then the offline data flow. 10 gigabytes per second come out of HLT2. Here we have calibration full events written to tape. They can also be called parked. They are parked there for a bit, and then sprucing can run over them and perform a dedicated selection. The output is again put in streams, and these streams can then be read by analysis production, and further the user can analyze this data. So there are some knobs here that you can turn. You can we don't only have these free streams. The streams could be set up differently. This is all configurable. Now some details on HLT1. The application is called Allen after the software engineer Francis Allen. The picture is on the right. And Allen can run standalone. It can be a standalone program that you can run on CPUs, or it can also be integrated within the LHCb software stack, and then it will depend on Gaudi, on LHCb, and so on. And can be run single or multi-threaded, can be compiled for GPUs and CPUs, and has all this flexibility. And this is also because we want to run Allen in simulation, and since the simulation runs at the grid, we don't have enough GPU resources, so there Allen would run on CPUs. So in the online environment, the event builder nodes are running standalone with multi-event packets as input. And these multi-event packets are is data that is streamed from the detector and assembled in the event builder. So you don't run event by event. You run really a bunch of raw detector data sequenced. You put this together, and you need to transpose these multi-event packets into something that is where you put all the detector robins together, so that the events are aligned. And in this transposing step, you get something which is called MDF format. And the MDF format is then something that is event by event. So this happens in Allen. You get something get these multi-event packets. You build them together, you transpose them, and you write out MDF data. And here is how such an MDF file looks like. So this is if you look into one of these MDF files and you search for the Odin bank, then you see that that the bank has an header with a size, a type, and a version, and then it has a payload, and here this is essentially this encodes information, which run number it was, which event type it was, at which time the event was taken, bunch ID, bunch crossing type, and so on. So this gives you information about the event itself. And this is all encoded into this raw data format here. And essentially this is how all the detector raw data will look like. So this is what we usually call raw banks.
Can I have a quick question?
Yeah, sure.
So you're saying that we have these multi-event packets, which are essentially different events compiled into a bunch, and then you get them to Alan, which then converts them into this MDF file, right? So it becomes just singular events from here on out?
Yes. So the multi-event packets, if I understood this correctly, are they have a header, and by this header you can identify, okay, this data was taken at this event number, and it has that and that many, typically 1,000 events just from one subdetector, from one tel 40. And you align them from all the other subdetectors, and this happens in the event builder, and then the data is sent to Alan, but still in this map format, and then Alan itself transposes it. So you essentially get aligned maps over all subdetectors, as far as I understood it, and then you write out an event by event format.
Makes sense. Thanks.
And there are details here in this technical documentation. So all these blue things here are clickable. Okay. Alan itself adds very little to raw banks. What is added in Alan are just the routing bits, DEC reports, and cell reports. The routing bits, they just define how the data will be processed. So will the data be physics data? Will it be monitoring data? So you can do some selective monitoring with the routing bits. Will it be calibration data? You can also say, okay, I had some errors while processing it. I want to stream out the errors, because sometimes the errors just happen very rarely. And you can write out an error stream by that. So these are the routing bits. Then the DEC reports, they encode which trigger lines have fired. So it's just yes or no on selection, HLT1, track MVA, for example. And the cell reports can, so they store at least the LHCb IDs, but they can also store more information. And this is everything that Alan writes in the end. So it just passes through the raw data and writes these 3 raw banks. So there's minimal amount of information added. In HLT2, we get the MDF data. All algorithms that are running in HLT2 are steered from Moore, and Moore just hosts the configuration. This is Python configuration that determines how you run your Gaudi algorithms. Online, you will run Moore asynchronously on the buffered data. So we have this buffer sitting there. You can wait for alignment. You can wait when resources are free, and then you will run HLT2. And if you follow the commissioning this year, you will notice that this data can sit a bit in the buffer. Okay. The main limitation of HLT2 is bandwidth. And bandwidth is just the processing rate times the event size. So you have two knobs to turn. You can turn the processing rate. You can turn on the event size, but this is limited to some extent. You can increase the processing rate however high you want, but eventually you will be limited what you can write out to Discord data. And on the right side, there's the concept of turbo and of selective persistence. So what is shown is 3 times the same event with different persistency options. The first one is called turbo, and only the solid objects are saved. So in this case, you would save 2 primary vertices, your information on the D0 candidate, and on its children. This would be all that is saved by turbo. Then we have something called selective persistent. And in the selective persistence, you might want to save tracks that are within a cone of your D0 candidate. So they fly roughly into the same direction. So you might want to have information from them. And the last one is persist reco, and there you would store everything that was reconstructed in this event. So all the reconstructed objects would be stored together with your signal candidate. And below here, you can also see that you can choose, in principle, you can choose which raw banks you want to save. So if you want turbo selective persistence, you can choose, but I also want the Velo raw bank in case you want to find if there's not another track coming from this D0, for example. So the reconstructed information, this would be the D0 candidate and its children, and also other things from the PV. They will be added to the DST data raw bank, and HLT2 will add the DST data raw bank. It will also update the routing bits or add HLT2 decancel reports. And offline, this I said already, sprucing will pass through the turbo data. We'll just do nothing with it. Yeah, the sprucing, I think this will also be covered in a follow-up talk. This will also use more of essentially the same framework as HLT2. So if you're familiar with sprucing, you are also familiar with HLT2 and vice versa.
Good question again, sorry. So you have those 3 options over there, and I just wondering who gets to pick which one do we?
The analyst.
The analyst.
Yeah, the analyst can say, I need this, and of course there will have to be some discussions about the bandwidth. For D0 to K pi, this will be a bit problematic if you want to store everything. If you have a rare decay and your trigger rate is per mil of a hertz or something, then it's no problem to write out more. Yes, but you have the freedom to add more objects to your candidate, and not only this must not only be reconstructed objects. You can also compose. Can run your own reconstruction algorithm and store objects from that, for example. So this is it should have all the flexibility you want. Okay, since the first slides were quite heavy and there were a lot of things to understand, I chose to make a quick intermezzo here. So this is how RTA is organized. There are 6 work packages. There's a coordination. There's an institutional board who coordinates how much people you can put on certain projects, connections to other projects. the implementation is then via PKs, shifters, developers, and so on. And since this year, we have 2 new coordinators. This is Carla and Michelle. Yeah, the work packages, and there are usually weekly meetings on the work packages, and there's also an RTA general meeting on Friday. And here you can also see who are the corresponding liaisons of the working groups. And the people of RTA, they also organize the software, and here's the structure of the LHCb software stack. Not all of the projects are shown there. There are many more smaller projects, but I hope I managed to pick out the most important ones here. So there are some framework application, some framework libraries like Gaudi, LHCb. Then there are component libraries. This is essentially the C++ code that does the reconstruction. Here you can also see that there's some simulation code building on LHCb and Gaudi. So this runs the event generation and the propagation through the detector. Boole does the digitization. So this is the simulated detector response. And yes, so these are the dependencies, but they do not mean that that they do not say anything about the data flow. So in simulation, you would run Gauss, then Boole, then Rec, then Moore, and so on. Okay, and all these projects are hosted on GitLab, and they are deployed on CVMFS either as nightlies or in periodic releases. The developers usually use the LB stack setup if they want to develop something bigger. Some quick developments or some quick checks can also be done with LB run or LB dev, where you can choose the nightlies or any quick version, any different version. Okay, so Ellen, I've talked about Ellen, that it can also run standalone. Then it would be completely detached from this tree here. And then we also have the online framework, and Moore Online eventually will run Moore in the online system. So this is what will run during data taking. And Moore Online also runs Ellen. Okay, now I want to go through the individual algorithms, or through the main algorithms that actually run in the trigger. And this is just a reminder of the type of tracks we have, because most of the algorithms will be tracking algorithms. So there are just, if you only have hits in the Velo and make a track out of it, it's called a Velo track. Then you have an upstream track with Velo UT. A long track is then formed if you add information from the sci-fi, and then there's a downstream track, which usually happens in k-short or lambda decays, where you only have information of the UT and the sci-fi. And then there are standalone T tracks, which are also becoming more and more important in the reconstruction. So what can we actually run at 30 megahertz? This is the HLT1 menu, and essentially HLT1 is a data reduction step, and the data reduction will happen with the global event cup and the event selection. And this event selection is based on tracking and lepton identification. So this is from the TDR, and this is what was there in the TDR. So you go from raw data to the decoding, to the tracking, fitting, finding primary vertices, and so on. Going through the step, you you can end up with long cracks and muon ID. By now, there's also colorimeter decoding and colorimeter reconstruction in HLT1 running. And with the second GPU, there are even more possibilities. So we are looking at removing the global event cut. We are looking at downstream tracking, at loosening the reconstruction. So you could reconstruct lower PT tracks, for example. In HLT2, you need to reconstruct with offline quality. And you have there are dedicated reconstruction algorithm, and you have a very diverse set of selections, which means that you have lots of branching. This branching is bad if you want to run your code parallelized. So if you want to do the same instructions with a lot of events. Still in HLT2, most things are vectorized by the so-called SIMD principle, single instruction, multiple data, which increases the throughput. So this is the sequence of HLT1. A tip would be if you use for example VS Code to follow the configuration. In the configuration, you will see what is actually running in HLT1 and HLT2, and things like VS Code should allow you to click through the configuration and actually see which algorithms are running under which conditions. And if you are developing things in HLT1, HLT2, it's very often helpful to look at tests, at tests that exist, and I will talk about tests a bit later, and follow their examples. Most of the time, or yeah, really often, you will find existing tests, and you just need to modify a few things for your use case. Okay, now the first algorithms that are running are the decoding algorithms, and I've talked about bandwidth already, and about how the Odian raw bank looks like, and essentially decoding means the data comes encoded because it is in some compact data format. We cannot afford to push around lots of data, so we have a very clever way of writing our data so that it uses the least space possible. Okay, you can get even further reduction if your detector front ends already do zero suppression. If they say, okay, we only record hits above a certain threshold, and you can even do some clustering in the front ends, or in the case of the Velo on FPGAs, and this will be happening before HLT1, and thus you have some more free space in HLT1. An example here is the UT hit encoding. It's a relatively simple example in the sense that what you want to get out are just single strip hits. So the UT is a strip detector, and you just record where locally did the particle traverse through the UT. So in this case, this is a single event, and there's a header. The header contains the payload of what will follow. So here in this header, you say there are so and so many hits in lane number 3. So the data is grouped in a certain format, and every subdetector has a different format. In the UT, this is grouped by lanes. You have a certain number of hits in lane number 3, a certain number of hits in 2, 1, 0, 4, and 5. And then you have the event ID also stored in this header. And this event so every tel 40 of the UT sends a certain sends this kind of information. And with the source ID of the tel 40, you can say this came from a certain region of the UT, and together then with the information of the strip ID, together with the detector description and the alignment conditions, you can say the hit was exactly coming from this XYZ position. And then you have other than the strip ID, which is this 11 bits, there's also an ADC count that you can encode here, and this can then be used in the clustering and then in the construction later. So if you compare this, one hit has 16 bits, and an int usually on a modern computer takes up 32 bits, a double 64, and so on. So this is we have our own formats, essentially, how we encode the data. Okay, I said already this is just the example for the UT, and the other subdetectors. They have a special format, but the simplest the concept is very similar. Now on to the velo tracking. The challenge in the velo tracking is combinatorics. You have on the order of 100 hits per layer, per plane. Sorry. So each of these stripes here is a detector plane, and there are 26 of them, and 2 modules each. So these are these L-shaped modules here, and you can move them apart. This will also be shown later. The GPU and CPU algorithms for the velo tracking are very similar. They operate on a 4-plane sliding window. They first built hit triplets, and they use the phi proximity. So in the first plane you would pick a hit, and in the second plane you would pick a hit that has a similar phi. And so in the third, and this reduces already the seeding step, the combinatorics of the seeding step. And then you extend this always by 1 plane, and you stop if no hit is found in 2 consecutive planes. But also these 2 consecutive planes, you can configure this later. Once you've done this pattern recognition task here, you do a straight line fit of the output tracks. And these you will then use in the PV finding algorithms, where you have tracks going forward and tracks going backward. And what you do with these tracks is you fill a track density histogram. So you calculate the points of closest approaches to the beamline, and you histogram this up, where you expect that tracks coming from a PV have a are very close to the beamline. And so you get out a histogram like this, and note that this is very zoomed in. So this is minus 50 to 30 millimeters, and the full velo range, actually not sure, it's, I think minus 200 to 700 millimeters or so. So this is a very, very small range. And here you see that there are actually 3 primary vertices that will be found here by peak finding algorithms. And these peak finders, they give you the position of the seeds, and then as a subsequent step, there's an actual vertex fit performed with the tracks that will give you a better actual position in 3 dimensions. Okay, the challenges for run 3 is that we will run at about 5 times higher PV multiplicity than in run 1.2. So if you are doing analysis, the PV misassociation could be a problem, especially if you look here. If you have a secondary vertex, it's easy probably that it can point back either to this PV or to this one. So this can be a problem then later in analysis. And then there's so I've said this PV finder here uses the beamline. There's also a more expensive algorithm. This is a 3D PV finding algorithm that we've used in the commissioning of this year's data taking, because yeah, the beamline position was not too well known sometimes.
Sorry, just kind of, what were the sort of the blue lines of the situation? What are the red lines on this document?
I think the red lines are called regions, and I think they are simply defined by minima between peaks. So you will segment this into regions, and then this is probably important for the fitting step later, but there I'm not 100% sure. I think if you go through this figure here, and the figure probably points to other documentation, you get more information on that.
So they basically define the areas where you have 0 effects.
Yes, where there's a very low track density, and I can imagine that this is then helpful for the vertex fit later. Okay, now we can move on to long tracks. And here we have 2 algorithms. One is the forward tracking, and the other one is seeding and matching. So in HLT1, you need to run either or because you have a throughput constraint. In HLT2, you will first run seeding and matching, and then forward, and then the forward runs on the leftover velo tracks and leftover sci-fi hits that the hybrid seeding didn't use. And here you can see the evolution of this. So the forward tracking starts from velo tracks. No, sorry. This is already seeding and matching. So hybrid seeding will build your T tracks. You take the velo tracks reconstructed in the step before. You match the standalone T tracks to the velo tracks. You filter out the velo tracks that have not been used, and they can then be used in the forward tracking, and both give you long tracks. Without the UT, we had to be quite flexible, and the configuration is set up such that you can easily switch between all the possibilities that you can run here. And also now HLT1 is looking into running first the forward, then seeding plus matching, or the other way around. Okay, so the concept of the forward tracking is the follows. You take a velo track that defines some search window. So you have this huge search window. You take you look at all the hits in the search window, but you take the magnet as an optical lens. So you have an effective kick position, and you calculate the simplified trajectories, and then you look at the hit projections. Should we? And then there will be a half-light transform along these simplified trajectories. So you register the number of layers in a histogram at a certain reference plane, and when there are peaks in this Huff like histogramming algorithms, then you will pick up the hits along this line. Do we need to move the?
Yeah, I don't have the converter with me.
I also didn't bring any power cables. Sorry.
Is your laptop for some reason?
I also job.
Can try to switch on mine in parallel and see how we can go with this. Otherwise, I'll try to speed up. Now is the okay. I'll continue with the seeding and matching. The goal of the seeding and matching is first you build the standalone T-tracks, and for that you search for hit doublets in SciFi's T1 and T3 layers. So this on the right you see one of the 3 T stations, and you would, for example, take a hit in X1 of this T station and a hit in X2 of the other, and you assume a minimal momentum and that the track origin is at 0, 0, and from that you search the hit doublet. Then you look for matching exits in the second tracking station. You get the remaining 2 hits from a parabolic fit. You remove outliers, and then flag the hits that won't be used in the next iteration. So you do this this step here 3 times, and each time you do it, you relax the momentum search windows, and you also alternate the X layers. Okay, and by that you only have used the X layers so far. So you want to add information of the U and V layers. They are tilted a bit, and from the U and V layers you get information on the Y position of the hits or of the tracklet. We have some issues with the projector. And it's okay. I hope we resolve this technical issue. So now that we've added the stereo hits, we have some Y information on the T tracks, and there will also be some recovery step for low momentum downstream tracks that relaxes this condition that you are searching for tracks originating from 0, 0, 0. The matching algorithm that matches the Velo tracks to or the Velo or the upstream tracks, if the UT is installed to the SciFi seeds, will be a parametric one in HLT1. It can also be one that is assisted by a neural network, and this is the way it is running in HLT2. You get downstream tracks from the seeding and matching, from extrapolating the T tracks to UT and look for the hits in UT. Moving on to the ridge reconstruction. So the principle here is that you have remove this. That the Cherenkov light is emitted along a trajectory if the particle moves faster than the speed of light in the traversed medium. So we have this carbofluorides in the ridge, and our particles are close to the speed of light, so they emit Cherenkov radiation, and the mirror geometry in the ridge is such that the emitted Cherenkov radiations form rings. And you can even beautifully see these rings in the event display here. So the event display displays the decoded hits in the ridge, and you can see that there are some nice rings, and also in the planar projection here in the lower left, you can see nice rings, and you can also see that there's quite crowded area around the beam, more in the center. So how the ridge reconstruction work is that for each crack state at the ridge, there's a simulation running that generates and traces Cherenkov photons and simulates the detector response. What you then do is start with all the tracks being pions, and you compute a global likelihood. Then you change the hypothesis of no, I have to remember how you change the hypothesis, but I think you keep the ones that change the global likelihood most, and then you do this iteratively, and so you get a best global likelihood, and what you compute later is the differences of each single track with respect to the best global hypothesis. So for each track, you compute the pion over kaon, pion over proton, over electron and muon hypothesis. The next detector further downstream is the eCal. So photons and electrons, they just shower in the eCal, and they deposit almost all their energy. And this is not the same for hadrons. So you can discriminate photons, electrons over hadrons with the eCal. Electrons will be identified just as tracks that point to an eCal cluster, and you can also use the eCal to recover Bremsstrahlung. The neutral reconstruction works as follows. You cluster energy deposits, the so-called digits. So in this case, you would have a cluster map like this. You have 50 MeV deposited in this cell, 100 in this, and so on. So you have these digit values, and then the clustering starts with a seed cell, and these are the cells that form global maxima in a 3x3 window. So you make 3x3 windows, you search for a local maximum, and these are your seed nodes. And then you also notice that there are some bidirectional nodes. So the yellow ones, they point to two seeds, and you can have links to 3 as well. And by that you represent the clusters as graphs, and use the shapes to identify merged pair zeros, zetas, and so and isolated photons. Okay. Next particle ID is muons. There we have the is-muon variable, which is just a coincidence of hits in M2 to M5 in a planar field around the track extrapolation. So you have already a track. You make a search window in XY, and then is-muon is just the coincidence of hits lying in this field. Depending on the momentum, you require either 2, 3, or 4 consecutive hits. So these are some momentum steps here. So is-muon is a relatively easy variable to calculate. Then for run 3, there has been a new variable introduced, a new muon ID variable that supersedes the muon log likelihood, and this takes the correlated sum of spatial residuals into account. So what you see here are the residuals of individual hits, and these are vectors running over M2 to M5, and you compute this covariance, or you compute the chi-square using the covariance matrices that take multiple scattering into account, as well as the hit correlations and the off-diagonals, and then you have this kind of similarity transform to compute the chi-square, and this is something that that you will see often in the tracking. This kind of transforms to compute chi-squares. Which brings me to the track fit. So this is a quite heavy subject, but I try to still introduce it. The goal is to determine the most accurate estimates of the track parameters and the covariances. And what you use in the track fit are the collections of lines tangent to a track trajectory. So if the particle has made a nice, however shaped trajectory at each point of its way through the detector, you can define a tangent, and this is called state. And you can parameterize this by the x position, the y position, the slope, and x and y, and q over p. And this state will have a covariance matrix. So then the combination of a state and a measurement in the detector, this is called a node, and this node will be used in the Kalman filter. The Kalman filter then will add measurements node by node and minimize the chi-square on the track in 3 steps. So if you go from a node k-1 to a node k, then you predict where your track state will be at k, and this is this xk k-1. So you see that this is a relatively large prediction, because you have also added some noise qk to the covariance matrix, and then the second step is a filter step. This adds information of the actual measurement at the node k, and so what you end up with is this filtered state xk here, and this has a lower uncertainty. And then you go to the next layer and so on. So this is an iterative procedure. If you have done this for all the measurements, then there's a smoother that will give you the best estimates of all the states and uses through the information of the previous nodes. And if you sum up the chi-square of this, you will get the track chi-square. Okay. So the concept of the Kalman filter is then also used in the alignment of the trackers. So why do we need alignment in the first place? This is because the detectors are really exactly there where we expect them from the description database. So in the description database, you say module X is at a certain place, but it can actually be rotated. It can be moving with time, and you see all the ways of the detector movement here on the right. So we have some translations along all the 3 spatial coordinates and some rotations. The tracker alignment for Velo, UT, Cypher, Muon finds at most free constants for the translations, and it also at most free constants for the rotations for each alignable element. And these constants will then be exported to a database that can then be picked up by, for example, an HLT 1 or 2 job that is running, so that you don't only take what is in the detector description, but also you take the alignment into account. What is done technically is that you insert the alignment constants into the track fit, and then you iterate the smoothing step with a global covariance matrix of track states. And you can also do this by using constraints. So this is really you make the track fit more complicated by floating up the covariance matrix, and then you fit with several tracks in the event, and you see how which is the best chi-squares you get out for your tracks.
Question. So when you're talking about these alignment constants, do you mean, like, for example, if the detector is moved like 1 millimeter in the X direction, then you say 0.1 millimeter?
Yes, exactly.
Okay.
It's nothing more than that.
Okay.
Okay. One thing that is a bit special in LHCb and that I would like to highlight here is that the Velo can open and close, and it can do so when LHC declares stable beam. So here you have a nice display of the closing monitor, and this is so if we will take data again, then you see that the Velo will move towards the center, and you see the parameters, and actually this thing will look like the Velo is really closing. So what you do is you align the translation constant of the Velo halves, and you check that this alignment works by reconstructing PVs independently for the Velo A side and the Velo C side. And you do this delta PV X versus right, and here you see that in the simulation there was some they simulated some offset, and after alignment this has been fixed. The infrastructure of the alignment and calibration is the following. So for different detectors, this happens at different time scales. At the beginning of a fill, you will align the Velo and the trackers. At the end of each run, you will run a ridge calibration. The ridge mirror alignment takes a while, so this will happen during the fill, as well as the muon alignment, which runs in the monitoring, I guess. And the calorimeter calibration takes quite some time, because they calibrate with pi zeros, and they calibrate individual regions of the calorimeter. The alignment and calibration also makes use of the dedicated streaming, and also has dedicated resources that they can use online. Now something on the selections. This is something that is discussed quite frequently recently. I repeat again that in HLT2 mostly they are bandwidth constrained, and these impose that the selections get tighter and that you move to more exclusive selections. And also here flexibility is the key. It's really important. There's then let me comment on some technical things. There's much branching in selections. This is especially challenging for GPUs, and the selection framework actually is quite different if you compare Allen to Moore. So in Allen, you just build all the combinations beforehand and then filter later. And Moore is usually also the CPU implementation is usually faster when you break early, especially if you have 3-4 body combiners. Things like that. Currently in HLT1 there are about 40 physics lines. In HLT2 we are at about 1,500. Most of the B physics is actually covered by the HLT1 track MBA and the HLT1 2-track MBA, and also the topological lines in HLT2. If you're interested, they use a neural network that fulfills certain properties, and is used to have an easier life later when you do your analysis with the efficiency correction. Okay. So another technical remark is that the throughput constraints don't really allow for a track or a vertex fit in HLT1, whereas in HLT2 we use the PR-Kalman filter, the concept shown earlier, and we also use so-called particle vertex fit that is run by the particle combiner. Don't have the time to go into the details about this. If you are interested in vertex fitting, you can read this in the note. The HLT1 selections are really written in CUDA itself, so you have to touch the CUDA code for this, and HLT2 uses a Python interface. Some of you might have written already some HLT2 selections. It's in Python, and it uses under the hood. It uses these 4 functors and combiners that are SIMD, that are based on SIMD, and they're written in C++. There are several documentations about this. So there's the Allen and Moore documentation. Currently, there's a hackathon ongoing to write HLT1 lines, and there were also I've also given a starter kit lesson how to write HLT2 lines some time ago. And I'm sure liaisons can also help with writing selections. So on the technical side, you can reduce the bandwidth further by packing and optimize streaming. But most of the optimization really will have to be done by the analyst. So you should, in 2023, it's important that analysts look at the data as soon as it comes, and then try to tune their selections. And this is really a great way to contribute to this year's commissioning. Okay, so then there are also special ways of operating LHCb. There's an upgraded SMOG2 system, which allows LHCb to run in a fixed target mode. And this is actually possible in parallel with P physics data taking. And this is great. You can see it here on the right plot that the beam gas collisions are really displaced from the nominal PP interaction, and they add actually little overhead, and so they can be operated at the same time. And actually, LHCb holds the record as the highest energy fixed target experiment. This was also something I didn't know before. Another mode of operation is the heavy ions, and you can also run in different settings here. You can have proton-lead collision, lead-proton collisions, lead-lead, and these are so they have very high occupancies in the detector. So these lead collisions are quite heavy. You see that LHCb really lights up when it sees these heavy ion collisions. In last year's data taking, there were unfortunately only 2 fields and there's more expected. I think a total of 4 weeks, if I'm not mistaken, for this year's data taking with heavy ions. Okay, these are now some slides on the software infrastructure. Not sure how we are doing time wise. If I should I keep going about the
Yeah.
So this is about the tests I've mentioned earlier. If you're developing, you can look up existing tests and develop from there. So the basis of this are these QM tests, quality management tests. And what you do in this test, you run, for example, the PV reconstruction on some simulation sample, and you compare a previous build to the current changes that were implemented. And you can really go down to the level of comparing counters or comparing efficiencies. And then you see in our nightly builds that the build here was all green, but in this case, for the online package, there were some failing tests, for example. And this is important, so we know instantly that nothing breaks our software. There are several flavors of nightly build, so you can change the platform, you can change the branches from which you are running, you can change the compilers, you can run special compiler instructions like sanitizer builds to find memory leaks, to find to really make sure that the code you will commit is sane. And what extends this nightly tests and this CI tests are periodic tests. They are also called performance and regression tests, which run on larger input samples and where you can make some more fine-grained studies of the code changes. These are usually scheduled. They can also be on demand, and they are in controlled conditions. This means if you want to run a throughput test, you want to run always on a machine that is empty, and that you get some sane throughput numbers. And here's an example on the left of the throughput of the HLT2 sequence, and you see the breakdown of the algorithm. So most of it is currently taken by the selections and drag fit ridge and so on. So these are the algorithms we went through before, more or less. I think we didn't go through the proto-particle building. And you can also run tests that check the rate of HLT2 lines and how large the output of HLT2 lines are, and so on. Then we also have physics performance tests, and these are very close to the plots you will see in Monet. They essentially use the same underlying algorithms, and you can see here the output of such a performance and regression test. And they are also, I think they are run weekly, and if something changes in these tests, this is also reported in an RTA meeting. So these were close to the online monitoring. Let me come to the online monitoring now. Online, there's a dedicated monitoring farm. This is these are essentially a few farm nodes are dedicated for monitoring, and the monitoring tasks can run their own sequence. And last year, they essentially each ran from their own software stack. Usually, these monitoring tasks take about 10 kilohertz of raw data, and the histograms will be saved around every 10 minutes into root files, into safe sets, and then you can analyze also these safe sets if you are in the online system. The history mode will also pick up the save steps. But when you are live, then this is really displayed live and not from root files. Okay, then I've mentioned this a few times. I think that there's the flexibility to run a dedicated stream of events. So if you set some special HLT1 routing bits, you want to filter very high PT events, for example, and only want to monitor them. This is what you can do. Okay, that brings me to the summary. I hope I've convinced you that with the upgraded detector, LHCb faces a very exceptional technical challenge, and you can see it also here on this plot. If we compare LHCb to other experiments, we are really pushing towards the highest trigger rates, and we also have moderately large event size. So we need both. We need really fast triggers, and we need to be able to store the events. So RTA responds to that challenge with a full software trigger, a heterogeneous software trigger, and provides all the flexibility that is needed to cover the physics program that is always expanding. The RTA project has huge overlap with detector simulation, computing, online and offline. It's really paramount that we all work together on this challenge. And I think this year's commissioning will really be a fun and rewarding challenge for everybody. And yeah, I really look forward to meet many of you in the control room. Thanks.
Thank you, Marian. It's been a great talk, very informative. So let's go ahead with questions, maybe. Maybe starting with the room first. Does anybody have any questions for the time being?
I had one. So, like, as I understand it, given that we've taken out L0, or triggers up entirely, so and as I understand it, the reason we have two levels there is because we can't decode and reconstruct like rich and ecal, is that correct? HLT1.
We could, in principle, we could do this. ecal is decoded in HLT1, and there's also I think electron reconstruction is running. Not sure. I think then there are even the first photon lines in there. The rich reconstruction would take a bit too long. Yes.
Well, my question is, do you ever foresee in the future we'll move to one kind of software level trigger, or do you think that's just impossible to do actually?
That's very interesting question. So you would, there are certain things you can do better on CPUs and on GPUs, but in principle it would have also been a two-stage trigger if we would have left HLT1 on CPUs if it was like in the past. So I think part of the answer lies also in the way that it's quasi real time. So you want to have a bit of buffer where you can run the alignment and update everything to go to a full event reconstruction, to go to the full reconstruction that is run in HLT2. Putting all this together into one stage is very challenging, and essentially the sprucing is something like HLT3 if you want. So, it makes sense to segment this to some extent, but not.
Fair enough. So I guess we can move on to questions from Zoom. So if you have a question, just raise your hand. Or you can just speak out straight away. I don't see any hands. Well, I did have another question, but it was it's not really related to RTA. If you can go to the slide that had the rich reconstruction. Yeah. So I was just wondering, maybe it's just me, but I feel like towards the bottom you have more events, or more. It's busier down there compared to up there. Does this maybe have anything to do with charges? The fact that we have proton-proton collisions causing one of them, like the bottom, have to be more positive and the upper part might be negative.
I think it's in this case it should be a fluctuation.
Okay.
That you just have more tracks towards
towards
I think if we would have the bending plane is horizontal.
Mm-hmm.
So this should be the segmentation in Y, and this really means that it cannot should not be from charge. It should just be
just fluctuations.
Just a fluctuation.
Makes sense.
Unless there's anyone to.
Sure.
It was basically just so I think there's all these numbers like that going there at the 40 megahertz, which is collision rate, and then 30 megahertz. The HLT1 actually operates that. So is there still some sort of L0 type thing in there that cuts the rate from 40 to?
I know. There are just 10 megahertz which are essentially empty, or which are so much forward that they are not in the acceptance. That's everything.
And then maybe one last question from me is maybe if you can say how we can contribute to the real-time analysis project. So I feel you guys need a lot of help nowadays, and
Yeah.
it is a good idea to get it contributing. And
I think one of the biggest challenges that we will face this year is monitoring and monitoring fast, giving fast feedback to the sub-detectors. This was something that that was a bit slow in the last year. So now that we have the issue with the velo, that the RF foil is bulged. Apollo approached me, for example, and said we need a displaced vertex regain. We need I think this can be done in monitoring if you write out a stream for that, dedicated stream for that, and you map out the RF foil in the monitoring already. So this is a great task if you want to do something more technical. Then the bandwidth division will be a huge thing. If not should be a huge thing in this year. I think we are a factor of 5 or 6 too high. But okay, there are some easy factors you can reduce there. We have many lines that were written for early measurements that they simply know they have too high rates, but they also have it's good that they have these high rates, so you can really look at the data fast and get some signals for feedback, and with time these rates will reduce, but still they're factor 5 or 6. Maybe they reduce a factor 2 or 3, but then there is still something that needs to be done there. So every analyst that has contributed with the line should look at the data as early as possible, and yeah,
makes sense.
Give feedback.
Sounds good. All right. Last call for questions on Zoom. All right. Seems like there aren't any. Last questions here. All right. Looks good as well. So thank you again, Marian, for the great talk. And stay tuned for the next talk, which is going to be the final talk of this current series. and is going to cover offline processing. So that's going to be sometime late next month. So we'll send an email detailing when that's going to be. And thank you for tuning in, and hope to see you in the next talk.
Thanks. See you.